All right, everyone. Thank you for being here today. Before we get started, I'd like to, just recognize Canonical for making this all possible, bringing us out here, and giving us the opportunity to talk to you about how software operators can help reduce complexity and friction in the HPC environment. My name is James Beedy. Alongside me today is Matheus Tosta. We're from a company called Omnivector, and we specialize in creating a suite of products that are geared toward HPC enablement for small companies, medium-sized organizations, and enterprise organizations as well. So, a little more about Omnivector. We have been a company a little over 3 years, and we've chosen to focus on a group of problems we were presented with and work on building solutions that solved a certain set of problems in the high-performance computing space. We have a cloud high-performance computing platform called Vantage. We provide consultation services in the design, operation, and maintenance of high-performance compute infrastructures. And we support these infrastructures via an enterprise SLA for organizations who need guaranteed uptime and guaranteed support on their infrastructure and their systems. So, what makes a computer high performance? This is an interesting question, as we all can perceive performance slightly different depending on our, relative to where we stand. And so generally speaking, I like to think of a high-performance computer such that it is a computational resource that demands more than can be had from a single machine. And to solve problems of certain sizes, oftentimes we need to use more than one machine. So this is kind of what our suite of software and services are focused around, is enabling these solutions to come into effect by reducing friction in the way we get from point A to point B. And so a little bit more about that, what we can kind of move into now is talking about how we got to where we are today. HPC was traditionally pioneered by companies that built systems comprised of specialized processor architecture and specialized hardware components geared toward solving a certain type of computational workload. What has happened over the years is we've experienced a shift to come to the place where we are now, where high-performance computing is primarily done using Linux systems and commodity hardware. This creates a large advantage for both software application vendors and ops and engineering teams alike, as software vendors now get a generic interface to compile their software against. Ops and engineering teams now can maintain systems with far fewer unique complexities and can stand on their kind of trusty Linux skills to bring things home. That's where we are now, is using Ubuntu to deploy HPC workloads and to assemble HPC systems. HPC is used across a variety of, the majority of major industries, such that benefits or, advancements in HPC in one industry may very well benefit the other industries that utilize high-performance computing as well. And that's kind of where our suite of products come into play. They aren't really geared towards one industry, but all industries that use HPC can benefit from the Omnivector Slurm Distribution, which was really what we're here to talk to you about today. And So the Omnivector Slurm distribution may be the product, but reducing time to market is the problem that our product solves. And it does this in a kind of a few different ways. The other problem we're here to talk to you about today is overspend in high-performance computing environments. This is another problem that the Omnivector Slurm distribution solves by reducing friction and enhancing operability across day two operations. And so, speaking about operations and high-performance computing and how we got to where we are now and the problems that we're solving, we try to think about what the largest problems are. And this is actually counterintuitive to the presentation, but can anyone in this room take a guess at what the most expensive line item is on the board here today? You would think energy. Some may think hardware, but the answer is actually software licenses, unfortunately. Aside from software licenses, operational costs account for around 60% of the overhead involved in running a high-performance compute environment. And so the operational costs are what we're focused on kind of reducing with the Omnivector Slurm distribution. But the software licenses are something that we've built a very unique piece of middleware to help companies reduce spend on as well. We'll talk about that a different day. Anyway, as things stand, we can also think of the cloud as being a potential compute bank that if let's say an engineer might want to run a computation and know what the results are in a certain amount of time, well, if all on-site resources are consumed, this it may behoove the engineer or the team to be able to scale their computations into the cloud and utilize cloud resources when on-site resources are fully consumed. This being said, the Omnivector Slurm distribution, what Matheus is about to introduce you here right now, is not only something that reduces time to market and reduces capital spend in HPC environments, but it also provides a hybrid workload solution to enable engineering teams to scale workloads from on-site into cloud infrastructures. Matheus, would you like to take it away?
Yeah, please.
Please.
So the Omnivector Slurm Distribution, as we usually call as OSD, the acronym, is a Juju charm. Simple Juju charm can be publicly accessible in Charm Hub. And I'm going to dive a little deep into the details and solving real problems with the OSD. Great, so introducing a little bit more, what is Slurm? Because OSD is Slurm Omnivector Distribution, right? So Slurm, basically Slurm is the acronym for sorry, I forgot. Can you help me? Simple Linux Utility Resource Manager. Excuse me, gentlemen. And the idea of Slurm is very simple. It's to comprise workload management like CPUs, GPUs, nodes, licenses, any kind of workloads in this context. And basically, Slurm has 4 components: Slurm Control D, DBD, Slurm D, and REST D. Can you go? Yeah. Okay, good. So the use case for software operators, what actually the OSD does, it comprises Slurm into a software operator. And to reduce the complexity, to manage the HPC environments, which are very complex, and to also help to manage the day 2 operations, the software life cycle itself. And the result is simple. It will reduce the capital spend for an HPC environment by enhancing the operations. Okay, so what about the cloud coverage? The Omnivector Slurm Distribution can be deployed in many clouds. Like this is just a few examples, okay? Like LXD, GCP, AWS, VMware, and vSphere, Azure. You know, this is just a few examples of it. Okay, so how about the modus operandi? How it actually works? So everything starts with Juju. Basically, OSD is a Juju charm. In Juju, also the second part is the operator framework. And basically, the operator framework is a Python package maintained by Canonical. It can be found on GitHub. And the idea, it is an event-based framework that ties into Juju's systems. So the Omnivector Slurm distribution uses Juju to handle the events. And by the operator framework, we can make the Slurm components to communicate each other. For example, I just said Slurm is comprised into 4 components, right? Slurm control D, Slurm D, DBD, and rest D. Let's say Slurm rest D needs some kind of information from Slurm control D. The way they are communicate themselves is by integrating these 2 frameworks. It could be a private key, configuration file, any sorts of things like that. We put all this together. We have the Slurm charms, the Omnivector Slurm distribution. We usually name as the Slurm charms. It's a created suite of software operators to deploy Slurm. Okay, so talking all of that, how do you actually use what I'm saying? How do you use Slurm? So we're going through a very quick demo. It's not live, okay? So we are going to deploy Slurm on LXD containers, and we are going to submit a workload job by the Slurm REST-D API. Slurm REST-D is the HTTP API we can communicate with Slurm. So we're going to use it to submit a job, and then we are going to evaluate the results using Paraville. Okay, very simple like that. You go to your terminal and run Juju deploy Slurm. You have an Slurm cluster deployed. It could be on AWS, LXD, it all depends on you. Simple. And that's pretty much the result. Juju status after you do the Juju deploy, and that's it. You have your cluster running. You might wait for a few minutes so the LXD containers get all up and running, the configurations are done, and that's pretty much it. You have a cluster like very, very, very fast. So submitting a job, a workload job, a real job to Slurm. We omitted some parts of this for brevity of the presentation, like the script itself, the token, the username. These are kind of a little bit complex things. So that's it. It's a curl command against the Slurm REST-D API. The same can be done by using sbatch commands. Sbatch basically is the entry point for running Slurm workloads. And viewing the results after your job has run, you as an engineer for a company might want to see the results. In this case, we're using Paraville. Just to make some context about this workload, it can define it is publicly available on GitHub. It's the
Great question. You want
Great
me?
question.
You want to get it or me?
You go.
So, we've taken a long time to get to where we are now. We started out, initially passing all the information about every node that it needed to communicate to, let's say, to a different node through a Juju relation. This ended up, we started to realize that as our clusters grew and then as the amount of communications then kind of became more and more and more, it wasn't as efficient for us to send information via Juju relations and back and to and fro. So we basically implemented etcd as a key value store such that nodes could put their IP address and host name and maybe other information in that key value store when they come online. And then when our Slurm REST gets the signal that a node has, a unit of an application has joined, then it just sources the key value store to get all of the information about everything it needs instead of making its way around, gathering each thing out of the relation.
Following up on the same question, did you ever have to scale up etcd then in that case?
No.
No.
Even with many nodes, the etcd we're really just pulling and putting kind of one value per node really.
Yeah.
Okay.
And so we're not doing anything too complicated there. But good question. Thank you.
Anyone else?
Yeah, I was wondering what the specific use cases are for Slurm. Like you showed the simulation software, I think it was. What are other use cases?
Can I go?
Yeah.
So, if you go to Wikipedia, which I just did 3 days ago, searching for the biggest 500 HPC clusters in the world, you might see that 60% of them use Slurm. So you can literally use Slurm to run any job. Like, by job, what I actually mean, any computation workload. It could be simulating an airplane wing. It could be forecasting the weather, forecasting stocks, machine learning, deep learning, literally any job. You could just run Echo Hello World as well.
That's true. You can't just do that.
Very expensive Hello World.
Yeah, it is.
We actually have seen graphical application. Some organizations may want to use Slurm such that they can track the resources used by their engineers who are even just using GUI apps or using any kind of resource. It doesn't have to be a large distributed workload. It could just be you may want to track what different users, what resources users consume. Slurm gives you a very common sense way of doing that, no matter what your workload is. Joe.
Given that you've got the agility and repeatability to deploy, do you find that that's enabled you, or is much of your business sort of single jobs, even for someone who doesn't have their own HPC infrastructure? Say, I need to process all this data, and you can just do that, and then it goes away. Or do they tend to be long-lived, continuous use deployment?
Both.
Both.
Yeah.
Both, yeah. It depends on the organization's restructure.
The ephemeral workloads are mostly using cloud resources. So we've built some custom integrations that are not part of the Omnivector Slurm distribution that allow an organization to go from 0 nodes to running a full workload in the cloud based on just inputting a few parameters. How many nodes, what operating system, where the storage is located, and what have you. But on-site workloads majorly kind of sustain the node's life cycle. It doesn't power off very often, let's say.
Yeah.
Yes.
So I think you were the.
Mm-hmm.
Following the previous questions, I'm wondering how many instances the HPC instance deployed with Slurm are deployed with charm, this charm solution? Can you tell me that?
It could be, I mean,
A lot.
yeah. I mean, it could be thousands. It could be hundreds. It could be thousands.
I mean, you are talking the HA, the part of HA, but I mean, how many real world cases, which institution or organization are currently using your charm?
Hundreds.
Would you mind telling me that number? If no, it's okay.
I mean, we can say it's hundreds of nodes, for sure.
We take inbound contact from new people reaching out to us about this software quite often. So exactly how many are using it and where, I guess we don't really track that. But what we do know is that these it does bring in a lot of attention. We do get a lot of inbound contact due to people wanting to try this out or talk to us about how they can use it or what have you.
You guys try to look into what's your performance from cold boot to deployment? Because that's actually sometimes when you're talking about ephemeral loads, right? That actually becomes a very key point. Like you can't have something ephemeral if you can boot it up quick.
We do. With bare metal infrastructure, I mean, oftentimes the nodes need to be rebooted. So I guess like a critical component of the Slurm charms are some of the day two operations that we've built in. And a lot of those have to kind of, well, I said we wouldn't go live, but let's do it. A lot of, I guess, the day two operations may comprise things like rebooting, installing drivers and rebooting a node, let's say.
It could be installing a software the company might need to as well.
And so, you wouldn't want to add a group of nodes to a cluster that's running and have those nodes be immediately available to people who are using the cluster because they may need to be rebooted or some kind of post-deployment provisioning may need to happen to
I would expect that part to be handled by the policy for load balance.
No, but
I didn't want that transfer on that part.
yeah, but let's say your machine installs an NVIDIA driver. How is the load balancer going to reboot it?
Fair point.
You see?
John, did you have a question?
I have a question about how you found building HPC workloads with Ubuntu, right? So the HPC community more broadly has been quite centered around CentOS, I guess because of the kind of lineage from scientific Linux and such. It's increasingly simple for us to package things for Ubuntu and get things into the archive and build snaps and jars, but I'm interested in how that goes down. Like when you speak with a customer and say, hey, we're going to build your HPC cluster app using Ubuntu, how does that kind of go down? How have you had any kind of issues there?
Great question. Yes. The Omnivector Slurm Distribution is kind of it runs the same way on CentOS as it does on Ubuntu. So it's oftentimes the HPC applications that support not Ubuntu. And that is really what creates the demand and kind of the need for us to support other operating systems that aren't Ubuntu with these Omnivector Slurm Distribution. Honestly, we got here because of, it's a long, windy road. There was an initial creator of the Slurm charms who's actually sitting right here. A small part of it, yes, but many years ago, 5, 6 years, we basically started using some charms from Hunt University.
Someone in the Netherlands, I think.
In the Netherlands.
Yes,
And they didn't want these charms anymore, and we at Omnivector had a use case. So we basically took over maintainership of these older untouched charms and basically have built a whole suite of products around them now at this point. oddly enough, it started with snaps. The Ubuntu initiative. Initially, we wanted to snap Slurm, and we put a lot of snapping Slurm was a huge project for us for quite some time, and until it wasn't, and there are a number of reasons why it just didn't. It wasn't the right fit for this software, and but all the same, the in snapping Slurm and the Ubuntu ecosystem software that wasn't Snapcraft stuck. The Juju bits stuck, the Maz bits stuck, the LexD bits really stuck, and became an integral part of how we are able to produce this software.
So is it broken more that you essentially have your control plane in Ubuntu, like all of the Slurm itself isn't running the jobs, right? And you have kind of workers essentially on CentOS. Is that kind of how it goes down in the
100%.
Cool, thank you.
Yeah, right on.
Do we have time for more?
Yeah.
Do we have time?
We have, I think, one or 2 minutes. Are there any more questions? Awesome.
No?
Thanks, everyone.